Morning, everybody. Tomorrow's lab. Tomorrow's lab is Center of Mass. It's number 8. You have the lab packet for it, or you should. Yes, no? Yeah, right? I handed that out. Okay, so Center of Mass, I believe, is covered in chapter 9. Tomorrow's the only day that I, quote unquote, lecture on it. So it's information we save for lab. So the beginning of tomorrow's lab is going to be about half hour of instruction, and then we'll get into the lab portion, right? I'll teach you about center mass, how to calculate it, that sort of thing. So just be aware of that. Tomorrow's the only day for center mass. Let's see, what else is there? I think I did this calculation right. 2 weeks from this Thursday is your next exam. It comes up just a little bit quick in this unit. Okay, so just kind of be in the mental space for that. And I think that's it. You saw my announcement about GRASP on Friday. Okay, I'm not going to be here, but the room will be open at 8 o'clock.
Oh, okay, so the room's not going to be open around 7:30.
It's not open at 7 or 7. Yeah. I'm the one that usually comes in the morning, opens it early. I'm not going to be here. I get to have shots in my lower back this time. So, fun. All right. It is quiz time. Let's do quiz. Okay, so rotational kinematics. We're here. Let's pull out some old friends. I'll write them over here. Okay. Do you remember that one? Back when you thought physics was hard. And then there was the second equation and the third equation. Right? We had that toolbox right there. So there's the linear equations. So I could spend the next 45 minutes deriving the kinematic equations for rotation, but I'm not going to do that because you guys don't need to know the derivations. You need to know how to apply them. We're going to spend most of our time with application. So we are going to do the shortcut. It almost feels like cheating, but it's not, because it turns out to be what you get if you go through the long derivation anyway. So what we're going to do for rotational kinematics is we are going to go to a toga party. Yeah, what's a toga party? It's something that happened in the 60s and 70s, right? What's a toga? It's like a sheet that the old ancient Greeks would wrap around themselves, right? Because pants and shirts and things weren't a thing. So toga parties where you go dressed in your toga for whatever reason. It must have been fun. I've never done it. So what do I mean by that? We're going to go Greek. So we're going to copy our linear equations, but we're going to do it with Greek letters and the symbols for the analogs, right, in rotation. So instead of a V, be very careful. What are we going to use? It is not a W. Omega. Thank you. Gonna get mad now. So omega final equals omega initial plus, instead of A, it's going to be alpha. And then there's no Greek T, it's just T. Okay? Instead of delta x, instead of like a linear distance, what distance are we going to use this time? Delta theta, good. Delta theta equals omega naught t plus 1/2 alpha t squared. And then, not a V, omega final squared equals omega initial squared plus 2 alpha delta theta. Okay, let me ask you a question. Are the rotational equations different equations? Yes, but no. They are not different. They are like there's a screwdriver and a screwdriver. It's just one has a blue handle and one has a red handle. They are both screwdrivers, right? They do the same thing. Try, it's hard. It's really hard when you don't do this for a living, but you should try to see the fact that these three equations are equations that you already know how to work with and how to deal with. Yes, it's in a slightly different alphabet, but we're going to be doing the same things that we did before. Just a couple more things just to have sort of a complete toolbox, right, for rotation. Maybe I shouldn't do the line on the bottom here yet, okay, is we are going to include our sort of Google Translate, right, between linear and rotational things. We had that one, and I think we had this one, right? There's the one for centripetal acceleration. But we'll kind of throw those into the toolbox because they are useful for getting back and forth, right, between linear things and rotational things. All right. So let's do some examples of working with rotational kinematics. Okay, I'm going to use the example of a hard drive. These are going a little bit out of style in consumer electronics, a lot of solid state stuff nowadays, but still very much in use in network storage, data centers. If you've got anything in the cloud, which everybody does nowadays, there is a 100% chance it's being stored on a hard drive. So when I was back in community college, so warning, old man story coming, right? I needed money, and so I went and picked up a job at Seagate Technologies. They needed people to answer the phone in the, oh golly, what was the title? What was our department? It was pre-sales technical support. So I provided technical support for people before they bought a hard drive. That was a thing. So customers would call us up, and we did, most of the work we did was with big companies that were trying to install mainframes and stuff like that. And they would call us up and they'd say, we need this much storage, we need it to be this fast, and then we would sort of give them pricing for what kind of hard drives and what the performance needed to be and how they would put them in their arrays and all that kind of stuff. So that's what I did, and I had access to all the specifications for all the hard drives. What I've done is I've taken more modern hard drives. Most hard drives nowadays, decent performing hard drives, will have a spindle speed of 7,200 RPM. What's an RPM? Revolutions or rotations per minute, right? So literally, in terms of a unit, right? 7,200 revolutions or rotations per minute. Now, are those standard units right there? Not even close, right? And what kind of unit is it? Is it a distance? Is it a velocity? Is it acceleration? What do you think? It's a velocity, isn't it? Because it's got that distance per time, even though the distance is a little bit funky, right, as a revolution. So we're going to have to do something with that, right? What about the 30 revolutions per second squared? There's a clue. That's an acceleration, isn't it? Okay. So do you remember? So they're asking for, right here, how long does it take for the drive to start up? In a startup process for a drive, it needs to power on, it needs to calibrate its read-write head, and then it needs, and it also needs to speed up the spin, get the disks spinning from 0 to the final spindle speed. So we're trying to figure out how long it would take, right? If we're engineering this drive, how long is it going to take before this drive is ready to go? So we're being asked to find what? How long? What does that mean? Time, isn't it? We've got a velocity, we've got an acceleration, we're looking for time. Do you remember how we solved way back in chapter 2 and 4? What was our approach? When we were visualizing, what did we do? Yeah, we made a list, didn't we? We made a list of everything we could know and not know. We weren't able to do lists very well with Newton's laws because there's like two things, right? But like in kinematics, we've got a lot of data to keep track of. And so we made a list. And the list came directly from the toolbox, didn't it? So this list, right, if I kind of flip back to this toolbox right here, and I take a look at my things that I could know and not know, I'm just going to move through these equations and write down everything I could know or not know. So what is that? Okay, I could know the final angular speed. I could know the initial angular speed. I could know the acceleration, angular acceleration. I could know how long it's taking, and I could know how far it went in terms of angle. So I'm hoping right now that this is starting to feel maybe even vaguely familiar and that you're not having too much PTSD from the first unit, right? Now that you've been through the second unit, you're kind of like, first unit was easy, right? So what do we know? Do we know the final angular speed? Well, yeah, it's 7,200 revolutions per minute, but we don't know it in the right units, right? So let's go ahead and convert that right now. Let's just get the conversion out of the way. We know we're going to have to get into standard units, right? Okay, so minutes or revolutions first? Which one do you want to do? Minutes. All right, so for every 1 minute, how many seconds are there? 60 seconds. So we got to our minutes, didn't we? We got it into seconds. That's what we need. What's our goal here for an angular speed? What's the standard units for angular speed in angular terms? It's a radian per second squared, right? Okay. All right, so now we got to do revolutions. So revolutions, denominator or numerator? Denominator, 1 revolution down the denominator. And how many radians are there in 1 revolution of a circle? 2 pi. 2 pi, and you can go ahead and put RAD or radians or something there because human beings hate not having a label. All right. So the revolutions cancel with revolutions. I'm left with radians per second, and I can see what it is I have to do. 7,200 divided by 60 multiplied by 2 pi. And that will get me I don't know. Because I don't have the right numbers in here. Yes, I do. I just can't read. I was on the wrong problem. 754 radians per second. Okay, so I'm going to go ahead and put that over here. 754 radians per second is my final speed. What's the initial speed? What's the drive start at? 0. Alpha. Okay, 30 revolutions per second squared. Is that standard? No. Okay, so I'm going to convert this into radians per second. I don't have to touch the second squared, right? I just need to fix my revolution. So 1 revolution, 2 pi radians, and that gets me 188.5 radians per second squared. Now, some of you are sitting there going, Mr. Balogh, couldn't you just keep it all in revolutions? Like you go revolutions per second and then revolutions per second squared, and wouldn't my units work? The answer is yes, but there's a little bit of danger there. You can't use revolutions per minute and revolutions per second squared in the same problem, right? The time unit isn't the same. So my default answer for beginners at this is to just go to the standard unit. You're always safe if you are in the standard metric unit because the equations are designed to be able to take those standard metric units through them. All right, so I've got 188.5. Now, is the drive speeding up or slowing down? Speeding up, isn't it? So what sign are we going to put on that acceleration? Positive, right? We say positive 754, and we're speeding up. We better have a positive acceleration. Okay, we don't know the time, and we don't know how far it went, right? We don't know how many radians it turned through. All right, we are looking for time. We know omega, omega naught, alpha, and we want time. Is there a tool that can get us what we want from what we know? First equation. Second equation will help us because we don't know delta theta. But the first equation is looking pretty good, right? So the plan is use the first equation, solve it for time, okay? Move the omega naught over, divide both sides by alpha, rearrange. Time is going to be the difference between those things divided by alpha. So what do I got here? I've got omega, my final omega, 754 minus my initials, 0, all over 188.5. I'm not putting my units in there because I have standard units, and I know I'm going to get seconds out if I put my correct units in there, and I get 4 seconds. 4 seconds. Startup time. That's about standard. It's average. Usually the motherboard is still running through some of its self-tests and doing things like that at about the same time the drive becomes ready. We don't really turn computers on and off that much anymore. We kind of put them to sleep instead. And if you have a solid state, then there's no waiting. Question?
It says 4.0
Seconds. It's just very messy. So you are correct to call me out on that horrible penmanship. All right. That was part A. We did that. The data error. Oh, okay. Right. So, all right. So hard drives store their information in a section of the drive, but it can't go too close to the spindle and it can't go too close to the outer edge. And so, like, if we sort of imagined it, it's like the data area like start and stops between those two arcs, right? It goes all the way around, right? And all the data gets stored in the in-between area. But there's an inner radius, right? Sort of an R in, and then there's like an outer radius where the data part stops, right? So they want to know, so they ask, how fast is the platter going? So usually, if you're being asked like how fast something is going, that's a linear speed question. Like how fast is meters per second, miles per hour, kilometers per hour, right? If they wanted to know the angular speed of the drive, well, they would say, what's the angular velocity or what's the angular speed? We already know what the angular speed is. No matter where you are on this platter, how fast is it going in terms of angles per second? 754, right? Like we know how fast it's going. It's going 754 radians per second, okay? Or 7,200 revolutions per minute. Okay, however, as the read-write head, it's hard to see on this picture, but there's this read-write head right there. And if we looked at sort of a side view, we'd have the platter, and then this read-write head is coming over the top, okay? It's got a little sensor on it, right? And when they talk about a hard drive crashing, that's two things. It could be a logical crash, which means like the software or the data that's running from the drive is being corrupted somehow. That's a logical crash because no physical thing has happened. But then there is an actual crash where the head impacts the surface of the drive and scratches it and destroys certain data areas. I paid my way through college after I transferred by saving people's data. I worked in the network operations center and computer technical support for the college, and many a graduate student that walked in with their entire life, their thesis, right, their PhD thesis, on a floppy disk. Our first question to them was, do you have a copy? No, my entire thesis is on this one little floppy disk. They're called floppy because what do? They flop. When you put them in a backpack, they bend or break or get dust in them. And so we would have the mental counseling to one side of the room, and then we would take their floppy disk and try to save it on the other side of the room. And we were mostly successful. at getting most of their theses back on track. All right, so we want to avoid tragedy, but what they're asking is how fast is like this point under the read-write head going? Like as it goes past the read-write head, like how fast is it going in meters per second? Okay, so that's what we're going to try to ask. So is there anything in the toolbox that answers like how fast in meters per second? It's sitting right there, isn't it? Okay, I mean you're like over here I can redo all these equations. You could redo all that. You could redo the problem in linear terms, but you don't have to. Do we know how fast it's going in terms of omega? Yeah. We can find how fast it's going tangentially, right, underneath that portion. So I'm going to use V equals R omega. This is a tangential speed. I know my omega, and I know each of the R's, right? They tell me that. So at the 1.5 centimeter mark, okay, what am I going to put in for the radius? Good. We have to convert, right, the centimeters into meters. It's important. We've got to be in standard units, right? So there it is in meters. And then we've got 754 radians per second. And since I put these in standard units of meters and radians per second, I'm going to get a meter radian per second, but a radian isn't a unit, right? So this will just come out in meters per second. It's like magic, but it's called science. So this is 11.31 meters per second. That's a 3. All right, and then the same thing for the 4 centimeter. That's going to be 0.04 meters, 754 radians per second. I got 30 we'll call it 2 meters per second. Okay, so at 11.3, this is approximately 25 miles per hour. At 30.2, this is approximately 68 miles per hour. So there's a big difference in how fast a piece of data is spinning underneath this read-write head. And so if you wanted to get the data quickly, where should it be stored on the drive? On the outer edge, right? Whereas data that isn't as important to access quickly or maybe doesn't get accessed as often, right, could be stored on the inner parts of the drive. And there used to be a process called defragging a drive where you would heal the drive a little bit and get it working better and faster by having the operating system shuffle information between the inner and outer portions of the drive and get files, instead of being spread all over the place, get them connected to each other physically on the surface of the drive. Now, this isn't the fastest hard drives. You can purchase right now, you can purchase 11,000, 15,000, and I believe they still have 30,000 RPM drives that are available. The faster the drive goes, the faster it can get information in and out. But a hard drive really can't match the speed that a solid state drive can. So if the best upgrade you can do for any old piece of technology, if it has a hard drive in it, is swap out its hard drive for a solid state drive. It's almost like a brand new computer. You don't have to change the processor, the memory, anything. The faster the drive spins, the sooner it's going to break. There's a statistical measure called the mean time between failures, the MTBF number. At 7,200 RPM, you have mean time between failures running into the 1,000,000 hours or so. But as you go to 30,000, the mean time between failures comes down to every 1,000 hours. It could be a failure. So they live fast, they die fast, right? But the performance is there if you need it. Generally, you don't go above 72 or even 5,400 RPMs in storage for long-term storage stuff because it's just really not necessary. The fastest drive that Seagate ever made, it was not a production drive, I believe was a 54,000 RPM drive. It was a prototype. It kept destroying itself. They would spin up the platters. The platters are made of a metal that has sort of a ceramic, like a glass coating to it. And what would happen is that ceramic or glass coating would fracture and just explode, okay, once the drive got too fast. What they discovered was the platter size and the speed that they were spinning it at, the metal was holding together just fine. And the ceramic was supposed to be able to withstand the incredible acceleration it was experiencing. What they didn't realize is that the outer edge was going so fast that it was breaking the speed of sound. Okay? And so the outer edge was going through the sound barrier, while the inner edge still hadn't gotten up, because the inner edge isn't going around as fast, right? Its tangential speed is slower. And so what would happen is there'd be like a mini sonic boom happening on the outer edge, which would start this undulation of the outer edge as it kind of bounced up and down, where the inner edge is going, what's going on, man? Right? And it would just this wave would propagate and just tear the whole thing apart. And so they started filling the drives with argon or pulling a vacuum, and that solved that problem. But then you can't ship a drive that's got a vacuum in it because the vacuum's going to break. It became a problem. So they just gave up on that and started using electrons instead in solid state. But solid state at the time wasn't very good. So anyway, just some insight there into computer technology and the direct application of what we are learning about rotational kinematics to electronics. This is something that actually shows up in your book in chapter 11, but I'm going to talk about it now because it can be very useful to know right now. You'll have a little bit more homework about it in chapter 11. I do want to talk about the specific case, right? Not just of something turning, like this wheel turning right here, but of it rolling, right, along the floor, okay? Because something special is happening here that we need to talk about. Because there is friction in this motion. Where's the friction? It's at the point of contact, isn't it? Okay. Now, if I had a frictionless table, right, what would happen to the wheel? It would just spin like this, wouldn't it? Okay. Or I would just pull it across and it wouldn't roll at all, right? But because there is friction here, the wheel, right, will roll with the surface. Now, what kind of friction is it? Good, it's static friction. Okay. So let's say this wheel is attached to your car, and it's going along. We're moving along at 25 miles an hour. Okay? Be careful. Think about this. How fast is the very center axle of the wheel going? If your car is going 25 miles an hour, how fast must this center axle, which is attached to your car, going? We're just concentrating on the speed that this part is going at. What does the answer have to be? 25 miles an hour. Why does it have to be 25 miles an hour? Because if it's not, then your tires are no longer attached to your car, right? Okay? So you would agree with me that the very center of this wheel is going 25 miles an hour. Okay. That seems reasonable, right? How fast, tangential speed, mind you, okay, is the bottom of the tire going where it contacts the ground? Stop and think about it. How fast is the ground going? 0. There's static friction between the tire and the ground. How fast is the contact point right here, this section of the tire? How fast is it going? 0? Okay, whoa. The middle's going 25. We know that because it's attached to the car, right? But now, Mr. Bailey, you're telling me this is 0? Yeah, why is it 0? This part's going 25 to the right, isn't it? As the wheel rotates around, how fast is the wheel going to the left? 25. But the whole structure has to be going at 25 to the right as well, doesn't it? So what happens if you have 25 to the left and 25 to the right down here? You get 0. How fast is the top of the wheel going? 50. 0 at the bottom, 25 at the middle, 50 at the top. Because there's a combination of translated motion, right? Your car, the center of the wheel, all the parts of mass, they're all going 25 miles an hour with the car, right? But now we also are rotating the tire. And so we have to kind of add in the velocities of that rotation as well. So in the case of rolling motion, and in physics what we mean by rolling motion, that is rotation without slipping. So this is no skidding, okay? This is static friction only, right? We talk about the speed of the center of mass, the center of the wheel. I know tomorrow we'll learn about center of mass, but it's the center, you know what center of mass is. It's the center of the thing, right? Okay, if it's the same shape all the way around. Okay? The velocity of the center of mass, but then we have different tangential speeds at the edge of the tire, depending on what part of the tire we're talking about, right? Okay, so how do we summarize all of that? Well, first we get a circle down. Okay, so there's the very center, right? And the velocity of the center of mass for rolling motion, and again, rolling motion means static friction only, right? So this is not a bowling ball, because bowling balls start with kinetic friction. When they leave your hand, it's kinetic friction between the lane and the ball. Eventually, at a point of roughly 2/3 of the way down the lane, that's going to switch to rolling motion, where there'll be static friction. But the bowling ball is wonderfully complicated physics. It's really fun. Okay, so the velocity of the center of mass is going to be r omega. Remember that? Remember that equation? Right? V tangential equals r omega. Well, it turns out that we can match how fast the center of the tire is going with its angular speed. I'm not showing you how that's possible. I'm just telling you that's the way it is, because we do have to get on with our lives and do other things, okay? But do note, right, that if the center, right, is going at some speed, we'll call that V center of mass, then the bottom of the tire is going at 0, and the top of the tire is going at twice the center of mass speed. Okay. And it's rolling without slipping. It's static friction only. There's no kinetic anything going on in here. And we will live well. Okay. So I just wanted to point that out, and that our V tangential equals r omega can also be used in rolling motion. So let's do an example where we've got some rolling motion. Again, your homework will be a little bit light on the rolling motion part, because this is covered more, and your text covers it in chapter 11. But I decided to give you a heads up here so that you're well armed for that chapter, but also it's useful in this chapter a little bit too. Okay? All right, so notice, what are they giving us here? We got meters per second. We got time, right? We got all it. So that sounds like a regular old kinematics problem, doesn't it? Only, what do they want me to find? Oh, jeez. Number of revolutions. Like what is that? In our symbols for kinematics, what would number of revolutions be? Is that omega? No. Is it alpha? Alpha's acceleration. No. So what is it? It's theta. It's the angular distance, right? Only theta is measured in radians, but we can convert into revolution. Okay. So they're asking me here for theta, right? Or like a delta theta. Okay. Final angular speed. Well, we'll do part B later. Okay, so, and again, we're assuming that no slipping occurs for this, for this tire. Okay, so there's two, we got choices now. We can do this standard chapter 2 toolbox, all that kind of stuff, and convert to angular. Or we can kind of convert to angular first and work it with the angular toolbox. What did I do? Oh, that's what I did. Okay. What do you want to do? Do you want to work it chapter 2 style, linear first, and then convert? Or do you want to convert first and then do angular stuff? Convert first? Okay. It's not what I chose to do, but that's fine. It's fine. Okay. So this 22 meters per second right here, okay? Like, what is that? Like, how do we relate that to our angular terms? I mean, it's a speed, but it's a very special speed. It's the center of mass speed of a wheel, isn't it? Speed of the wheel, speed of the car, all has to be the same. And that's equal to r omega. So I can find omega by taking the radius of the wheel, the other way around, by taking the velocity of the car and dividing it by the radius of the wheel. So let's do that. Okay, it's 22 divided, oh dear, 58 centimeters. There's two problems with that number. What's one of them? It's not in meters, right? So we got to convert the 58 centimeters to meters, right? But it's worse. What's the other problem? It's the diameter. I hate the word diameter because I never see it. I just put in, like I would literally just put in 58 right now for the radius and live my life, but it's not the radius, is it? What's the radius of the tire? The radius is 0.58 divided by 2, isn't it? So watch out. Diameter, radius, how easy is it to mess those up? Pretty darned. Hopefully you're smarter than I am. What the heck did I get for that? 0.29 is what I got. 0.29. Okay, so that should get me radians per second. Indeed it will, because meters divided by meters is nothing, which is a radian. I don't have this in my notes, do I? Yes, I do. What did I calculate? 75.9 radians per second. Okay. We know, okay, let's make a list. We know the final omega, 75.9 radians per second. What's the initial omega of the tire? 0, starting at rest, right? Do we know the angular acceleration of this thing? Did they give us, it's not 0 because it wouldn't be speeding up, right? So we don't know it. Do we know how long it took? 9 seconds. And we're looking for the delta theta, aren't we? That's what we're after. But what are we going to have to find first? Because it's everywhere in all the tools. We have to find that acceleration. So is there an equation we could use to find the acceleration? First one. The acceleration is going to be the difference divided by time. So we can get, let's see, that's 75.9 minus 0 all over 9 seconds. 75.9. This is where I don't have anything in my notes. I have no idea what this number is. 0.43? 8. I was going to say that sounded a little bit low. Although, yeah, GoodNotes is telling me that it should be able to do this. Yeah, but for some reason it did not detect that as math. It's been detecting everything else as math. Oh, there it goes. Nope. Here we go. Convert, edit, partial fraction. No, I didn't. Okay, I'll practice that a little bit more. I can't get rid of it.
White marker and color it out.
All right. We'll leave that as a testament to my stupidity and to not beta test beta features in front of the class. 8.43, we'll go with that. And then now that we know our alpha, how are we going to get our delta theta? Yeah, second equation sounds good because it's already done for me, right? Whoops. Omega naught t plus 1/2. By the way, I don't memorize a new set of equations. I actually wrote it down. I had to erase it. I think of it as delta x equals v naught t plus 1/2 at squared. But as I go, I just swap in the Greek letters, right? So in my brain, they're the same equations. Different coats of paint. All right. We know omega naught was 0, right? Plus 8.43 times, oh, I forgot the half. It's wrong order. 9 squared. This better be 340.7 radians. Yeah? Okay, we'll do 341. Slightly different way, so a little bit of round off error. Radians. And then they asked for revolutions. You're gonna be screaming at Wiley Plus about this, okay? Because it's gonna ask for all kinds of weird rotational answers. So now that I've got it in radians, how do I get to revolutions? 2 pi radians in 1 revolution, right? Go back to chapter 1. Do a conversion problem, and I got 54 revolutions. So you can do it either way, right? You could start with the linear terms and find out how fast the wheel's center of mass is going in terms of meter per second and then convert it into omega at the end. We did it this way. It's perfectly fine. It's good practice for the rotational stuff. We haven't answered the second question. What is the final angular speed of the tire? In revolutions per second. Why did you have to do that to me, Wiley Plus? Well, we found the final 75.9 radians per second. So how do I find 75.9 radians per second? How do I get this into revolutions per second? 2 pi radians on the bottom and 1 revolution on the top. And that should get us 12.1 revolutions per second. All right. I think, yeah, So that was kinematics. We did all of chapter 2 and 4. Well, no projectile motion. So, okay, all of chapter 2, right? And now we're going to skip. We're going to do Newton's laws next chapter. Because Newton's laws needs a whole chapter all by itself. What we're going to do is we're going to skip to energy and talk about rotational energy. So we know about kinetic energy. As this tire moves like this, does it have kinetic energy? Yeah, right? Its mass is moving at some speed, isn't it? Does the tire have kinetic energy now? Are you trying to tell me that this part of the tire right here has no kinetic energy as it moves around? Does it have kinetic energy? Yeah, it's moving, right? So it has kinetic energy. So we need to be able to deal with the rotational energy that tire has. Okay, so let's just be bold. Let's be brave. Let's be naive and see what happens. We got to convert this into rotational terms, right? Which means we can't have any V's in it. We need omegas. So how do we get from V's to omegas? V equals R omega. It's your Google Translate, right? We're getting forwards and backwards. Okay, so let's go ahead and drop that in here, 1/2 m, and then we got to square everything, right? So it's an R squared times an omega squared, isn't it? Okay, well, sure, but I don't like it. I mean, it's got the 1/2 in common, doesn't it? And it has the velocity squared in common. Like both of those are a type of velocity, right? Different units, different idea. One's going in a circle, one's going in a line, but they're still the same general category, right? So I got the 1/2, I got the velocities. What I don't have is like a mass sitting right. Maybe I do. Maybe I can hide it. Maybe I could just write, I don't know, a different symbol. Capital I. That feels a little bit better. I have a 1/2. I have a speed squared. And then I have a single thing sitting in between. This is called rotational kinetic energy. And I is rotational mass. What the heck is that? What's mass? Tastes like salt. The quantity, the amount of stuff in something, right? It's related to the inertia, isn't it? The more mass something has, the more inertia it has. More massive things take more force to get them to change their motion. That's Newton's second law. So I'm reaching for an idea that could capture that same sort of idea, but for rotation, right? Mass would tell me, like, if I apply a force to this thing, it would tell me how fast I can get it going, right? How much I can accelerate it, how fast I could get it going. But in rotation, right? Rotational mass would be how hard is it to get it to rotate, right? Regular mass is how hard is it to get it to move, right, in a straight line. But rotational mass would be how hard is it to get it to rotate. And what's more, we wrote down that it was mr squared, right? Leave a little space in your notes there between the equal sign and the mr squared. I mean, up to this point in this class, the shape has made no difference, right? If it was a tomato or an elephant or a Ford Bronco or a penguin or anything, right? It didn't matter. We just treated it, we drew it as a square, we treated it as a point particle, that was it. But now we have a concept, an idea about this rotational mass that depends on the radius, like where the mass is from the center of rotation. So for the first time in this class, we actually have to start thinking about the shape of an object. And what's more, this mr squared, it talks about like a single part of the wheel, right? It's this mass going around a circle, but right next to it, there's another mass that's going around a circle, and there's another mass going, what do I have to do if I want to add up a bunch of things that are pretty much looking all the same? It also starts with an I, ends with integral. An integral? If we add up all the mr squareds, where did I put this? Yeah, right here. okay? What's the little change? Well, here, we'll write it like this. We'll say add up all the mr squared, but really, if we wanted to push this to its limit, it would be r squared dm. And I know your brain just kind of went, because how do you integrate over mass? You're not going to really learn the answer to that question until Physics 4b, where we won't integrate over mass, but we will integrate over other things like charge and stuff, and it'll come back to mass just a little bit. But the actual sort of strict definition for the moment of inertia is that right there. However, we are not going to do the integrals. We are going to think of it, we're going to make other people do the integrals. That's what we're going to do, okay? And the way that we're going to make other people do the integrals is by having a table of shapes, okay? Now, this is the table in your book. I don't like it. It's too big. I don't like the font. It's got small writing on it. I like this one better. This comes from a different book, okay? And this is the table that I will give you on the exam. The last page of the exam is going to have this exact slide on it. And what this slide is the integrals done for us for various shapes of different things. So for example, if I wanted to find the moment of inertia, let's not do this wheel. This wheel's complicated. If I wanted to find the moment of inertia of a bowling ball, which shape do you think you might pick on the table? H, the solid sphere, because bowling balls are solid all the way through, right? Okay. And what does the table tell? Table tells me that the moment of inertia is 2/5 total mass, biggest radius squared. I don't have to go integrate anything, because I know that if the bowling ball being mostly solid, I know its mass, I know its biggest radius, that's it. Somebody's already done the integral for me, I'm done. Some of you are feeling ripped off right now. I take calculus for this class. Don't worry. Like I've alluded to before in Physics 4b, we will make up for this deficit in Physics 4a, and you will not be happy. Let's put it that way. Which one of these would you pick for a basketball? Because basketballs, being thin-walled hollow spheres, meaning the mass of the basketball is contained all the way out there in that thin edge, right? Filled mostly with air that doesn't really count. It's just all that rubber right around the end. Does it have a bigger or smaller moment of inertia? It's 2/3 mr squared here. Which one's bigger, 2/5 or 2/3? I failed fractions in 3rd grade. Obviously 2/5 is bigger. It's got a bigger number in it, right? That was always my argument. No, 2/3 is bigger, isn't it? Okay, so what the heck does that mean? What does a bigger moment of inertia mean? If these two things were the same mass and the same radius, which one would be harder to rotate? The thin-walled hollow sphere. Same mass, same radius. Like imagine a basketball, the mass of a bowling ball, right? Okay. This one's harder to get rotated. Everything else being equal, it has a bigger moment of inertia. Bigger. What? Which one's harder to push, a train or a car? A train. Why? Because it has more mass. Which one's harder to rotate, a solid sphere or a thin-walled hollow sphere? A thin-walled hollow sphere. Why? It has bigger rotational mass. All that mass is out there. I hate this building. There's no meter stick in this room. Okay, I'll use this. All right, it's a big meter stick, okay? This is going to be dangerous. Okay, yeah, well, something's going to get hurt. It's probably me. Okay, right? If I take this shelf and I rotate it through its center, do you see how I can rotate it through its center with relative ease? Physics, muscles, and all that kind of stuff, right? But like, I can rotate it through its center pretty easily, right? Okay? Where is this on the board, on the screen? It's not C or D. I know you want it to be C or D because it's flat, right? But it's not, because so C would be like this, right? Axis through the center, okay? I kind of did this, which is very similar, okay? But that's not quite it. So it's not, and D would be like that, right? It's much easier with a meter stick. It's A. This is A. I know I'm not a slender rod. It is, okay? Through its center, okay? But now I'm going to switch to B. Okay, A was 1/12 ml squared, right? B is 1/3. What's the difference? Where's the axis of rotation? Instead of in the middle where it's 1/12, I'm now going to do it around the outside. That was not an exaggeration, right? Okay? Right? Why is it so much harder for me to get this thing to turn over if I hold it on one end? I've got all of this mass at that radius, or L squared, right? So moment of inertia is trying to capture that idea right there. Did I change the mass? No, I changed where the mass is, okay? It's distance from the axis of rotation. So moment of inertia doesn't depend just on how much mass you have. Mostly it depends on how far away you are from from the axis of rotation. What is the mass distribution like? Back to the wheel, because I said it was complicated. What would you pick for this wheel on the table? G or E. Is it F? No. Is it solid through here? No. But it's not really thin-walled, is it? Like, is the mass of this bicycle contained only out here? No. It's not hollow. Do we need to integrate? Yes, but no. Yes, but no. Because this wheel consists, make it bigger, of a tire, a hub that's supposed to be in the center, and then spokes, I'll just draw 4 of them. So what could we pick for the tire? The thin piece of rubber around the outside. mr squared. So the tire, I would use mr squared. What would I pick for the hub? Yeah, solid cylinder. Down, right? And so that's 1/2 mr squared. So my hub is 1/2 mass of the hub, radius of the hub squared. Because those are different, right, than the tire. So we'll put tire and tire up there. And then what do we do for the spokes? By the way, you're never really going to use these two, so don't look at them. Is it A? No. Where's the spoke rotating? On its end, isn't it? So it's 1/3 ml squared. So this one is 1/3 ml squared. What's this one? 1/3 ml squared. What's this one? Same thing. What's this one? Same thing. So the total moment of inertia for this wheel is the integral of all of these things. In other words, you're not going to do an integral, but you are, because what are you going to do with all those things? You're going to add them up. And this is exactly what you can do. We're going to do this in the lab eventually. So we have mass of the tire, radius of the tire squared, plus 1/2 the mass of the hub, radius of the hub squared, plus 4 times 1/3 mass of a spoke, length of a spoke squared. Why was it 4 times? There's 4 of them, right? Okay, so we can make very complicated structures by putting together individual elements of this table, right? Okay, you're going to want this table. Like in your notes, it'll be available on the PDF for the lecture. You're going to want this table in your notes. Put it on your bathroom window. You don't have to memorize it, but it is so useful that you're going to want to have quick access to it, right? You're going to want to be able to look up the common moments of inertia, meaning common shaped objects, so that you can quickly put things together and find out what this moment of inertia is. All right, I want to set something up, okay? Because we now want to sort of take this, right? Because now we know that rotational kinetic energy is a thing. However, conservation of energy tells us work other plus energy initial equals energy final. Ooh, remember that? Work other. What did we always put into work other? If it wasn't a spring and it wasn't gravity, it went into work other, right? So all frictions went into work other, didn't they? What kind of friction is this again? Static. This does not go into work other. The static friction that causes this wheel to roll is handled in the kinetic energy rotational term. So even though there is friction, friction is required for something to roll down a hill, isn't it? We don't have to put that into work other because we have a new question to ask now. When we sit there in the initial energy and we ask, is it moving? What do we now mean by moving? Is it moving in a straight line? That would be 1/2 mv squared, right? Is its center mass, is the bulk of the thing going somewhere? If that's happening, then 1/2 mv squared exists. But what's the follow-up question? Is it rotating? Now, it can be rotating without translating. That's the technical term. Translation is to move in a straight line, okay? Rotation is to spin around in a circle, right? But translation is to move in a straight line. So you've got to ask yourself, Is something moving in a straight line? Yes or no? If it is, 1/2 mv squared. But also, is it rotating? And it can have both, it can have neither, or it can have one or the other, right? It depends on the situation of the question. If it's rolling without slipping, what do you have? Is there kinetic energy? Yes. Is there rotational kinetic energy? Yes. Notice when I say kinetic energy, I mean 1/2 mv squared. To be very precise, I should have said, is there translational kinetic energy, right? But we generally don't use the word translational very often. If we just say kinetic energy, we mean, is it moving in a straight line? But then we'll be specific. Is it have rotational kinetic energy? So in full, in the biggest we could have, right? We could have work other. Whatever that is, F times D for whatever's going on. Rocket motors, toy helicopters, friction, whatever's going on. Kinetic friction. Plus, and for the initial energy, we could have 1/2 mv squared, v initial squared. We could have 1/2 I omega naught squared. We didn't use knots. We used initials and finals in the energy chapters. Initial. We could have potential energy gravitational, and we could have 1/2 kx squared, which is what? Spring potential. Those are all possibilities now for initial energy states, right? You really hope that you don't have all four in one problem, because that's a bad day. And then on the other side for the final, same things with finals on them, right? Hopefully, again, some of these going to 0. But that would be like the whole enchilada right there for energy. 1/2 mv squared. What question are we answering? Is it moving? Is it center of mass going somewhere? 1/2 I omega squared. What question are we answering? Is it rotating? Because now we know about rotational energy. MGH, what are we asking? Is it at 0 for gravitational potential energy or not, right? And then 1/2 kx squared is a spring compressed or stretched, right? Those are all the questions you ask yourself, but the setup for these energy problems is the same. So what I'm going to do on Thursday, I didn't get to do it today, I'm going to do a demonstration of conservation of kinetic energy and some calculations and some examples of that. And then that pretty much winds up chapter 10 once we get through the energy stuff. Yep. Oh no, I lied. So we'll do energy, and we're going to get started on forces in rotation, otherwise known as torques. What are we doing tomorrow in lab? Center of mass. It's the only time you're going to get lecture on center of mass. So be there, or be square, or round, or rectangular, whatever shape you want to be. See you tomorrow.